Welcome everyone. So today we are going to talk about some of the properties of means, and I will create another video and focus on properties of variance / standard deviation. Standard deviation is just the square root of the variance. So whatever we do for the variance, it's not going to be hard for us to figure out what should happen with the standard deviation. But first I want to begin with a general concept that I believe is extremely useful in mathematics in almost every course you will take now or in the future. And that is the concept of a linear operator function. Or linear operator is just a function, and if it obeys this rule, where a and b are just constants, they could be also zero, it's just real numbers. If a function obeys this rule, we call it a linear operator. And sometimes this is heavy on students because I'm trying to do two things at once. I'm splitting, right? I'm splitting the pieces. It's almost like distributing the function. We're not distributing the function, but it looks like it. But also pulling the constant out, right? Pulling the constant out. If this is too heavy, you could break it down into two pieces. One just splits the function, and one takes the constant out. A is a constant, and x and y are variables or random variables. Now, by the way, whatever works for the plus works for the negative sign, because let me show you, because I don't want you to miss this one. If I have f of x minus y, it's the same thing as f of x plus negative y. And if this rule works, if this property is obeyed, then I can do this. And then if this one works, if I can pull the constant out, my constant is -1, so I can do f of x minus f of y, and therefore I achieved this fact. Okay, so whenever I put a plus, I also mean to refer to the negative sign. So that's kind of a given, all right? So if trying to show that a function that's f is a linear operator, you can do it in one shot. Try to prove that this is this, or try to prove this and prove that, and together will give you this. Okay, now why this breakdown is useful? It actually is more useful if you want to disprove this. So if you want to show that this is not that, it suffices to show that this doesn't work, or this doesn't work, or both. Now, if this doesn't work, you could just stop and say, okay, well, this cannot work because one of the pieces is violated. Okay, it actually is helpful to disprove this. More helpful to disprove than to prove. If I want to prove, I generally don't split it, make this work and make that work. I just go straight. But if it's difficult, you could split it, okay? Now, most functions that you have seen in elementary mathematics or a little more advanced like calculus, most functions don't obey this rule. And I'm going to give you some examples that don't work, and I will conclude with some examples that do work. I would say 95% of the functions are not linear operators. So I picked a few, just a few that came to mind. X squared. We know for a fact that ax plus by quantity squared is not this, right? Because the answer is a squared x squared plus b squared y squared plus twice a b x y, right? So we know this is not true. Now, to prove that it is not true, again, I could just focus on this, and that would suffice. So we know for a fact that, I'll put it in blue, x plus y quantity squared is not x squared plus y squared. In other words, this property, this piece of the property is violated. Therefore, whether or not this works, this doesn't work anymore, right? Because both have to work for this to work. It's almost like your parents, they both have to sign a paper so that the document is valid. We need two signatures. But if one of the signatures is violated, this is invalid, okay? So, now whatever I just did with the square works for any power actually, right? Well, with one exception, linear function, special linear function. So if I have x cubed, it's not going to work. X to the fourth, any polynomial, in fact, any power, x to the 2/3, it doesn't work. So I just gave you a family of functions that don't work. And x to the half is exactly this, right? So you know square roots of x plus y, square roots of x plus y, if you want to keep it simple, we know it's not this. We know that, right? So that doesn't work. If you pick log of x, we know it doesn't work. Log of the sum is not the sum of the logs, right? A log of a product is the product of logs, and even if that is true, you cannot just pull the a and b out. So even if this works, imagine the rule is this. Imagine, I'm not saying this is true, it's actually false, but imagine the rule is f of x times y is f of x plus f of y, then the log would work. But then it will violate this one, because log of 2x is not twice log of x. So even if we give it some credits, it's not going to work. Some exponential, 2 to the x, e to the x, 5 to the x, whatever, we know this is not true at all, okay? You will see, you don't know this yet, but you will see that the variance of the sum is not the sum of the variances. It can be true in certain situations, but it's not always true, so therefore it's false. False means it does not have to be true. True means it's always true. So keep that in mind. So the variance is not going to work. Factorial function. We know 3 plus 2 factorial as an example. We know it's not 3 factorial plus 2 factorial, right? Because that's 5 factorial, which is 120, that's 6, and that's 2, and 6 plus 2 is 8, and 8 is not 120. So we know the factorial doesn't work. I picked a couple more. Trig, you could use sine, cosine, tangent, it doesn't matter. You know sine of x plus y, I'm only testing this, okay? I don't even have to do this. I'm just testing this quickly. We know sine of x plus y is not sine of x plus sine of y. You know that, right? So, and I can keep going. Almost, I would say, honestly, 95% of the functions are not linear operators. Okay, please don't confuse linear operators with linear functions. I never mentioned the word linear function. I'm talking about linear operator. You might say, what the heck that is? That is exactly this, a function that obeys this rule. And if that gives you a hard time, it's a function that obeys this rule, these two rules, okay? All right, so now let's go to something that works. And there are some, not too many, but there are some. The mean function, as I will show you today. The mean of a sum is the sum of the means. And also the mean of a constant x, I'll do it here. The mean of the sum is the sum of the means. And also the mean of 2x is twice the mean of x. Okay, I will show it to you. So we know, for now, we know that the mean function is a linear operator. If you took calculus, the integral of a sum is the sum of the integrals. We know this, right? So you get integral of AF plus integral of BG, and then you can pull the constants out, A and B. So we know this is true for those of you who are taking calculus. Pre-calc, we know limit of the sum is the sum of limits. Now these are not random variables anymore, these are functions, f and g, right? These are random variables, but these are functions. And a and b are still constants, real constants. Now, one thing that works, I said here that even linear functions don't work, let alone quadratic or cubic or x to the half. That's true. The only exception is linear functions of this type. That linear functions that don't have the y-intercept. In other words, they go through the point 0, 0. They do work actually, okay? So if f of x equals 3x, it will obey this rule, I promise you. Okay, you could test it. I did it here very quickly. I'm trying to see if this is true, right? Isn't that the question? Well, we know that this is f of x plus y, f of ax plus by, because it's just linear. and with m, right? F of x is m times the inputs. So m times the inputs is mf of that input. And we know for a fact that I can distribute the m. M is a number, okay? So I can distribute. But when I distribute and I get max plus mby, I can flip-flop a and m and b and m because multiplication is commutative. And we know for a fact that this is a f of x. And this is b f of y. So I just succeeded in going from I shouldn't use m here, sorry. I just succeeded in going from f of ax plus by into a f of x plus b f of y. I'll do a quick example for you, okay? So let's say f of x equals 3x, okay? Let's find out what is f of x plus y. Actually, yeah, let's split it. Now, f of x plus y is 3 times x plus y, according to the function. Isn't that true? The function says multiply 3 by the inputs. So we're going to multiply 3 by the inputs. Now, we know for a fact that this is 3x plus 3y. I have the right to distribute the 3, right? And then, we know for a fact that this is f of x and this is f of y, by definition. So the first piece works. Now let's try this one. F of ax, and I want to know if it is a f of x. That's the second piece, okay? So, what is f of ax? F of ax is 3 times ax, according to the definition. Now, since multiplication is commutative, I can permute a and 3. Permute means each one takes the other's position. So a takes the place of 3 and 3 takes the place of a. I have the right to do that. And that is a times f of x. So I succeeded in proving the second piece. I succeeded in proving the first piece. And therefore, this particular linear function, now 3 played no role. I could have had 4, I could have had 20, I could have had m, right? Therefore, linear functions of this type, they do work, okay? There are more. Here's one I just thought of just now. The derivative of this function is this. So I'm able to distribute the derivative and I'm able to pull out the a and the b, okay? So derivative works as well. Let me erase it, it looks ugly, but derivative does work, okay? Now, I am going to focus on this one because that's what the course is asking for, okay? And I will deliberately split it for you into these two pieces so we don't get lost, okay? So, let's imagine I have a random variable. Now we're back to stats. I have a random variable x, and I have n data points or n observations, x1, x2, all the way to xn, and I have the same thing for another random variable, okay? And I, just by definition, what is the arithmetic mean of x? It's just add them up and divide by n. And the arithmetic mean of y is just add them up, divide by n. I wrote this because I'm going to need them, that's why. What I want to do is prove that the mean of the sum is the sum of the means. Replace f by the mean, okay? So let's begin with the mean of the sum. And if I can reach the mean of x plus the mean of y, I have succeeded. What's the mean of x plus y? Well, by definition, it has to be x1 plus y1. That's the first term, plus the second term. And each term has a pair all the way to the last term. Now, addition is commutative. I can move the y1 here, I can move the x2 here. I have the right to say that 3 plus 5 plus 7 is the same thing as 3 plus 7 plus 5. I can commute with addition. We say addition is commutative. So I'm going to do exactly that from third grade. I'm going to have the x's by themselves and have the y's by themselves, okay? Now we know from basic algebra that a plus b over c is the same thing as a over c plus b over c, right? So I'm going to do this over n plus that over n. But that by definition is the mean of x. And that is the mean of y. So I went from f of x plus y into f of x plus f of y. Basically, I just did this with the mean, where the mean is playing this role. Now let's see if that is true. So that's the first part. We just did the first part, okay? The mean of the sum is the sum of the means. That's a fact. We just proved it, so you can use it anytime you want. And that's going to save you a lot of headache, by the way. All right. The second piece. I want to know if the mean of ax is the same thing as a mean of x. So what's the mean of ax? So every observation is called ax1, ax2, ax3, ax4, right? Just in case you got lost here. We know my variable, my random variable, is this set. So this variable has to be this one. The set of observations are these, aren't they? Right? So the mean of this random variable, this is a random variable. Just because it doesn't look like x, it's still a random variable. If x is a random variable and you triple it, it's still a random variable. So what's the mean of this? Well, you just add them out by n, by definition. Now, notice that a is in every single term. So we can factor out an a. Here's the a stays. And this is by definition the mean of the sum of x. Done. So the mean of ax is a mean of x. So if you combine part 2 with part 1, you got that for free. I could have done it directly, by the way, but I decided to slow down and show you the steps. So now, the only one I proved is this, and you can use it anytime you want. And the reason I only proved this one, because this is the one we're going to use in our course. And there will be another one with the variance. But for now, this is the one we're going to use. We don't care about these, okay? Now, so what are the properties of the mean? So what you need to take away is the stuff in blue. We know for a fact that the mean of a constant is the constant. If I have a class of 1 student and got 80 points, and I say what's the mean, arithmetic mean of his score, or as they call it, the average, well, it's just the score, okay? The mean of a constant is the constant. The mean of ax is a mean of x. I just proved it. And the mean of the sum is the sum of the means, and the same thing could be said about the minus, as I did on that very first page. Now, let's work out an example, and I'll call it the day, okay? So here's the example. Imagine I'm connecting C to F. C is the temperature in Celsius, and F is the temperature in Fahrenheit, and I believe you know this formula from I don't know, basic physics. All right. So let's say you happen to know the mean of C. Basically, the mean, the average temperature in Celsius. Let's say it's 25. And you want to know the average temperature in Fahrenheit. Okay? So what you do is you begin with the formula. You always begin with the formula. And you introduce the function. In this case, it's the mean. Introduce the function on both sides, just like you did log of f equals log of that, or this squared equals that squared, or square root of that is square root of that. We are introducing this function this time. I am interested in the mean of f. That's what I'm interested in. But I know the mean of c. Do not say, oh, I know this. The mean of c is 25. You don't see the mean of c right there. The way you see it is if it looks exactly like this. Mean of C. If you see this, you have the right to call it 25 degrees Celsius. If you don't see this, you have no right to draw that conclusion. So right now, I don't see the mean of C. I see a little bit, but this 950 is bothering me. So we're going to slow down. We will begin with the sum. The mean of the sum is the sum of the means. We just proved it here, part 1. The mean of the sum is the sum of the means. So I'm going to do the mean of this plus the mean of that. Do not take the 9/5 yet. You've got to begin with the sum. So the mean of the sum is the sum of the means. We know the mean of a constant, C is your variable, okay? C is your temperature in Celsius, okay? The mean of a constant C is the constant mean of C. That is part 2. The mean of a constant C is constant, the mean of C. C is your variable. So we know that. And we know the mean of a constant is the constant from here. And now I see the word mean of C. Now I have the right to replace it by 25. I shouldn't do it too early. A lot of kids, they just say, okay, 9/5 times 25 plus 32. You're going to mess up. Slow down. If you don't see this by itself, you have no right to call it 25. I see it now. I see it with the naked eye. Now I'm going to replace it by 25. And of course, I'm going to get 9/5 25 plus 32, which gave me 77 degrees Fahrenheit. Okay? So that is a quick example. And I hope this is helpful. And actually, I'm surprised that the video is short. Take care.